Hi, welcome to BC Video 9.5b Part 1, Introduction to Alternating Series Remainder. Okay, so this is straight out of the book. For a convergent alternating series, the partial sum Sn can be a useful approximation for the sum of the series, which of course makes sense. It's an infinite series, so if it is convergent, it's the sum of all those terms ad infinitum equals a particular number. So if you wanted to approximate it, obviously if you took the first, 50 numbers, you'd get a good approximation. If you took 500, you'd get a great approximation. If you take 7, you'll get an okay approximation, but you will get an approximation. But of course, it is an approximation, which means you're going to be off by so much. That's called the error involved in using the full actual sum is approximately equal to the sum using the first so many terms. So the error involved in using S is approximately Sn is the remainder, what they call Rn. So let's say n is 10. So let's say you use the first 10 terms. Well, obviously you're going to have some, you're going to be off. You didn't use enough terms. You didn't use all the terms. So the remainder is going to be the sum of all the terms, the infinite number of terms, minus the sum of the first 10. So this would be R10 equals S minus S10. So if you think about it, if you take all the terms and take away from that the sum of the first 10 terms, what you'll be left with, this R10, is the 11th term plus the 12th term plus the 13th term, etc., etc., etc. So here's the alternating series remainder theorem. If a convergent alternating series, and by the way, this right now is only working with alternating series and it has to be convergent. If a convergent alternating series satisfies the condition that an plus 1 is less than or equal to an, in other words, the terms are decreasing, then the absolute value of the remainder Rn involved in approximating the sum S by Sn is less than or equal to the first neglected term. So you'll notice here's this S minus Sn, they have the absolute value of it. Keep in mind it's an alternating series, so you never know if the next term is going to be a positive term or a negative term. So they're just using absolute values. So they're saying the absolute value of S minus Sn, which is equal to the absolute value of Rn, is less than or equal to an plus 1. Now, the thing I want you to understand is that when you have a series, your an plus 1 is the part attached to the negative 1 to the power. Okay, it's not the whole un, but the an, and you're going to go to the next term. So what they're saying is the absolute value of this, the remainder you have. So let me kind of write that out. Okay, so if you write it out and if you look at it this way, let's say you have summation n goes from 1 to infinity equals un. The sum of all of those terms would go on forever, plus dot, 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 right? So your un is negative 1 to the n times an, or negative 1 to the n plus 1, or n minus 1 times an. So the actual sum would equal the sum of the first 6 terms, which are these terms right here, plus the rest of those terms. The rest of those terms is what's called the remainder, and if you use the first 6 terms to approximate the series, then the remainder is called R6, and R6 actually represents the 7th term plus the 8th term plus the 9th term, etc. So what they're saying is that the sum of all the terms minus the sum of the first 6 terms, which is their S minus Sn, the absolute value of that is equal to the absolute value of the remainder of the 6 terms, right? So if I take the S minus S6, I'm left with R6. And we're saying that that is less than, the absolute value of that is less than or equal to an plus 1, okay? So here's an example. So if we do use the first 6 terms, the absolute value of the error is going to be less than or equal to a 7th. That's not the 7th term, it's actually the absolute value of the 7th term. Notice how here I'm saying that an plus 1 is really the absolute value of un plus 1. Okay, so if you look at something like number 37, it turns out that the seventh term, so if I did this, it's S is approximately S6, and we use the first 6 terms to evaluate. I'm not showing you that here, but if I took this question and just wrote out the first 6 terms and added them together, I would get this approximation. Now, because I use the first 6 terms, the absolute value of the remainder of those 6 terms is less than or equal to the absolute value of the 7th term, or A7. So what is A7 in number 38? And let's have a look at number 38. So in number, wrong book. There you go. Don't need this book, do we? Number 38. Oh, also the wrong book. Never mind. Anyways, the formula for the term was obviously 4 over the ln of n plus 1. So the 7th term, well, the absolute value of the 7th term is 4 over the ln of 7 plus 1, which is 4 over ln 8, which is approximately 1.9236. That is the maximum that we are away from the actual sum. So the actual sum lays between this approximation that we got, 2.7067, plus or minus this remainder. So if I actually added these things up, that would mean that the actual sum is somewhere, not that this is a great example, but is somewhere between 0.7831 and 4.6303. Okay? And that's the answer given at the back of the book. So it's interesting because that's not the question. I'm going to pause for a second here and pull up the textbook. Okay, so if we do look at the book, okay, it doesn't really tell you that's how they want the answer. All it says is approximate the sum of the series by using the first 6 terms. And here's the question we were looking at right here. So this whole thing is our UN. If we ignore the -1 to the part, the rest of it, the 4 over the ln of n plus 1, is actually RAN. So in my opinion, approximate using the first 6 terms, in my opinion, the answer is 2.7067. What they should have said is, include in that the remainder. So once we get this answer of 2.7067, it's going to be plus or minus basically the absolute value of the 7th term, and that's how you get that answer right there.